Hey everyone, this is Nico from SILCARI Farm. I wanted to give you guys a tour of my off the electrical grid solar system. I've been living off the electrical grid for about 8 months. There's definitely pros and cons, which I'll probably make a separate video for to go into detail about those pros and cons. I'll try to keep this one short if I can. I wanted to give you guys a tour of the devices that are used and how it's put together in general. I know when I was doing my research to put together my own system 8 months ago, I searched the internet far and wide, and the information is scattered. There's a lot of misinformation, wrong information, and people giving advice based off no experience. So I'll try to add to the internet some beneficial information based off experience. I'll flip the camera around here in a moment so I can show you the instrument panels and all the devices, and I'll try to explain each one of them. I hope this video will help if you are one who is watching this video to try and learn something to put together your own system. I hope I can benefit you or teach you something. So I'm in a steel shed. It's kind of a junkyard in here at the moment. We're in the process of building a home, so that means the solar panels are strapped to the roof and not on the roof of a house yet, because that house doesn't exist yet. Well, let's get started. So basically on top of this roof, and I may go out to take a picture for you or add it to the video of those solar panels. I have 10 320 watt solar panels. The brand name is Renogy. I was pleased with the quality of the panel, the rigidity, the hardware that it came with to assemble the panels. So those are quite nice. They're fairly large. They're about 3.5 by 5.5 feet. So they take up the whole span of this roof. It's a 20-foot ocean container. The way those panels are wired now, there's a difference. If you're one who's looking to put together a system, be mindful of the difference between series and parallel wiring. To optimize the cost and performance, you're most likely going to be using both, a combination of series and parallel. If you wire in general, here's a footnote: if you wire in series, you're adding your voltage together. If you wire in parallel, you add your amps together. You double your amperage. Or if it's in series, you double your voltage. The way I have these panels wired, for every 2 panels, they're wired in series. Every 2 panels in series, so that's 5 arrays in series. And then those 5 arrays are again wired in parallel. What that allows me to do is keep my voltage high and my incoming amperage low, so that I can use smaller wire. Thinner cross section is what I mean. A smaller wire is cheaper, it's easy, it's more pliable, easier to work with, and it's safer. It's safer to carry lower amps and higher voltage than the other way around. If you have a higher amperage, that's a little bit more risky. This is 10 gauge, 10 AWG or 10 AUG wire, THHN wire. This is braided or twisted copper. This is not aluminum, although you should be safe using aluminum if it's available. Copper has a little bit better conductivity and performance properties, anti-corrosion properties, etc. So each panel is 320 watts, as I mentioned. It's, I think, 40 volts, 10 amps. So you stack 10 or 20 amps. I'll have to get back to that. Maybe I'll put the specs in the caption or footnotes of the video. So together, or total, I have 80 volts about 50 amps coming in, and that's at its maximum output. So I have these wires coming in. Let me step back here. See if you can get a good enough shot of that. Those incoming wires are coming into a circuit breaker, and this is a Midnight Solar circuit breaker box with 5 individual circuit breakers of 15 amps each. 15 amps, 15 amps. The Midnight Solar makes solar dedicated equipment, so I recommend this brand. The reason why it's sideways and not vertical is because I didn't give myself enough slack in the wire here to make that come around and underneath. So make sure you plan ahead and give yourself, I would say, whatever you think you measured, give an extra 3 feet. The cost of this wire is not much, and it's not worth the headache. I have 10 gauge coming in, 6 gauge coming out. The 10 AUG wire, or 10 gauge, I believe handles around 30 amps, and that's given according to your NEC chart, your National Electric Code. Be sure to check that while you're designing your system, so that you can make sure you give yourself an adequate wire thickness to carry the amps. Always go over. If you're going to give 20 amps or 30 amps, if you plan for 30 amps, go with a wire that can handle 40 to 50 amps, just to be on the safe side. Otherwise, if you have an event where you're soaking these lines with higher amps than they can handle, these will catch on fire. There's no point of having a circuit breaker if the wire that's bringing the charge is overheating. I think the 10 gauge handles about 30 amps, 6 gauge about 55 amps coming out, something like that. 4 gauge ground rod. So these circuit breakers control from the solar panels down into my charge controller. At any moment when I want to power off these devices, all I got to do is flick these circuit breakers to stop the incoming solar charge. You definitely want to put a circuit breaker after each main electrical device. So I have solar panels, circuit breaker, charge controller, circuit breaker, batteries, circuit breaker, inverter, circuit breaker. And the reason for that is you can isolate each component to your system. You have solar panels, charge controller, batteries, and an inverter. You want to be able to isolate those at any given time for service, maintenance, repair, etc. Or if you have some type of event, overheating, etc., you want to be able to service that and keep your units protected. Otherwise, if you had no way of shutting off your incoming power to your charge controller, you can have a lot of damage to the charge controller. It'd be nearly impossible to repair or operate on if you had a steady supply of current being delivered to it. So let's move on. So I got my phone turned around here, so I don't know how good of a video where I'm aiming. I can't flip my camera around, or at least I don't know how to. So we have incoming charge to the circuit breaker, and then we have 6 gauge coming out of the circuit breaker into a MPPT charge controller. Now the brand name is EP Ever. I recommend. They're a pretty good quality brand. Reasonable price compared to the other components on the market. Now there's 2 different types of charge controllers. There's the latest technology, I should say, MPPT, or Maximum Power Point Tracking System, and that basically just gives you let's say a real time or every 30-second tracking, depending on the sun, its irradiance, and how much power is coming in. it'll optimize the peak charging amperage to your batteries. If I can put that in shorter terms, it just does a more efficient job at charging your batteries. It keeps it safe because it has a temperature control sensor that monitors the temperature of the batteries. So if it's a really sunny and hot day and you're packing those batteries at 99 to 100% charge and it's just sitting there charging and charging, those batteries are getting really hot. What this will do is it'll back off the incoming current. It'll reduce it to its own algorithm to make sure you're not overcharging and damaging your batteries. The same thing goes if it's cold. The other version, or the older or more conventional technology, I believe is called a PWM, or a pulse width modulation, I believe. And that's just pretty much like a wide open circuit. There's no feedback loop with temperature sensors. It's not going to track for optimum performance or optimum charging currents. It's just going to let whatever's coming in, it's just going to pack it straight into the batteries. This is quite simple of a device. You have your 6 gauge coming in, and it has icons, which makes it easy for the installer of where you're incoming. These are your solar panels, your positive and negative coming in, and then your battery wires coming out, negative and positive. You don't want to get those crossed because you will damage the equipment. That's not covered under warranty. And this is also 6 gauge coming out. Now I only planned, I think, for about 60 amps coming out, but this is an 80 amp circuit breaker, just in case of a spike, I suppose. I gave myself a little bit more room to play with, so I'm not constantly tripping the circuit breaker. This is also flipped upside down, as you can see, so it comes in and comes out. Hey buddy, get out of here. So after your charge controller and your solar charge from your solar panels are passing through this controller, coming out, and they are going to my battery bank. Now this is the most interesting set of devices here. Let's see here. How's that video look? Apologies for all the junk in the background. I'll try to get that out of the video. Now, I have 8 200 amp hour batteries. These are AGM absorbed glass mat batteries. They are one of the safest sealed lead acid batteries you can have in terms of temperature shock. They're non-spillable, they're sealed. They won't explode as readily or overheat as readily. In other words, they're safe batteries. I'm happy with these batteries. These batteries are also from Renogy. Renogy is a company located in, I believe, Canada. They specialize in solar equipment. They're heavy. They're big, heavy batteries, about 130 pounds a piece. And again, just like the solar panels, the way you have these wired really makes a difference on the total performance and output. You can kind of see the combination that I have here. Let me get this flashlight fixed here. I have a combination of series and parallel. What you see here is 2 battery banks. You have 4 on the left side, 4 on the right side. Okay, and each 4 are wired in series. So those 4 are in series. These 4 are in series. These 2 banks together come together in parallel. I have, for my own decision and to stay safe, I put 2 300 amp bus bars. So when I bring these 2 banks together in parallel, you got to have some type of connection system so that the current flows in parallel out to your inverter, because you only have, to the back side of pretty much all inverters, you only have 2 spots, your positive and negative. So if you have 2 banks or 4 banks, you're going to have a lot of incoming wires that you have to reduce down to 2. So these bus bars you can find on Amazon, pretty cheap. I'm very happy with them. I think they were copper, like a nickel plated copper or something. Decent quality, really heavy gauge bus bars. They come with the lugs and everything, so it makes the wiring kind of easy for you. But they come up into these 300 amp bus bars, and then I reduce that into your 2 1/0 wires, or the 1/0 1/0 gauge wire. I think those can handle, oh boy, I'll get back to you on that, but well over 100 amps. So depending on how big your battery system is, you're going to want to make sure you have a decent sized wire to handle that current, because this is where it can get dangerous, is on the battery to inverter size. That's where you can have sparks and wires overheating and a lot more risk. Larger current, larger the risk. So this is 1/0. You can also find this wire off of Amazon. This is Southwire. The brand name is Southwire. I like this wire because it's a welding cable. So if you're looking for this type of equipment, look for a welding cable or a welding wire, because this is like a soft rubber. It's very pliable, bendable. There's some 1/0 and 4/0 wire that's just a really rigid coating, and you can't work with it too well. You can't bend it into tight corners. This is very pliable, so I do recommend a welding cable. 600 volts, that's well over my capacity, so I'm on the safe side. And because I have it wired in parallel coming up to the inverter, I kept my outgoing amperage low and safe. So basically what I'm saying is I didn't need to use the 4/0 wire. I can go as low as the 1/0. The 4/0, I believe the coating is a little bit thicker, and it's more expensive, so save yourself the cost on that. This is another circuit breaker that I installed to be able to isolate the batteries to the inverter, again for service and repair, etc. One of the last devices here is the inverter. Let me walk around. So this is a SunGold Power. That's the brand name. You can find it off Amazon. This unit was one of the most affordable units that I found. You know, each device has its own listing price, but the inverter is probably going to be one of the more expensive items in that whole system, and this was one of the most economical choices I could have made. I'm pleased with this product. I'd say it's probably one of the best performing products out of this entire electrical chain, because well, it's on 100% of the time, but it's taking the most abuse. This is a pure sine wave. This is a 240 volt split phase. So I have 220 or 240 volt plus a 110. I can service both. Pure sine wave. And it's also an inverter plus a charger, meaning it can be shored up to city electric. So I can use city electric if I'm hooked up to charge the batteries, if I didn't have solar panels. It's pretty much a combination unit. Let's see here, that's the outgoing side to my circuit breaker. Basically, just a simple circuit breaker, square D. I am servicing a well pump, a deep well pump, which is quite impressive for a solar powered unit. Most people on the internet would recommend not going with a solar powered well pump for just the heavy draw and the continuous use and just the overall performance, but it's been doing quite fine. I have a couple extra slots here, a pigtail slot for future use of something else. It's not being used. And then a 30 amp circuit breaker that's currently servicing the RV that we're staying in. It's more than enough power. 3,200 watts is more than enough power to service an RV. So there you have it. That's also 6 gauge coming into the circuit breaker as well. Maybe a few things that I forgot to add or wanted to point out at large here is that, again, I have 3,200 watts total available power of the solar panels. The 8 200 amp hour batteries that I have in 2 different banks, that's about 19,200 watts, watt hours, so about close to 20,000 watt hours. And since I forgot to add this in the video, when you're dealing with sealed or lead acid or AGM batteries, you can only bring those to about a 40 to 50% depth of discharge. So if your battery's at 100%, you can safely discharge those batteries to about 50%. For AGMs, maybe about 40. So that's a 70% discharge, leaving about 40% capacity left. If you go any further than that, often you can damage the batteries. If you have the alternative technology to the sealed lead acid, that would be the lithium. That's the newer technology. You can bring lithium from 100% charge all the way down to 0 and back up again every day without damaging the battery. That's quite a perk. The con to that would be the lithium batteries are about double or triple the cost of your sealed or your lead acid or AGM batteries. So be mindful about that in terms of your budget. They can, those batteries can add up and be quite expensive. Be sure you understand how much power you might need in terms of watt hours. You take your volts and your amperage and add it together, multiply it together to get your watt hours. This battery bank is also considered a 48 volt battery bank system, a 48 volt system. You have your 12 volt, your 24 volt, and your 48 volt systems. I would recommend you attempt to get to a 48 volt if you're trying to power a home or a large system. 48 volt will allow you to have higher voltage, and that means a lesser current. You're still having the same amount of watt hours available. It's just a method of how you bring that power to your inverter and your home. The higher the voltage allows you to use smaller wires, safer traveling current, easier to work with. If you had a 12 volt battery bank, you're sending a higher current, which you may have a lot more arcing when you're going to assemble your batteries to your inverter, etc. 48 volts a little bit easier to work with. And the inverter that I chose to go with was a 48 volt incoming system. So I acquired a 48 volt bank, and it's a 220 and 110 outputs. That's a split phase inverter. Everything is based on everything when it comes to designing your solar system, meaning if you have a large solar array, the array is what you call all the panels wired in series and parallel. You call it an array. If you have a really large array, 3,000, 4,000, 5,000, 10,000 watt output, you want a really large battery bank to go with it. And you also want the devices, charge controller, circuit breakers, and inverter to go with that output. If you have a really small array, you don't need really large charge controllers. Each charge controller has its own voltage and amperage ratings. Be mindful about that when you're designing. I would start with your batteries first and work towards your panels to make it less confusing. And the reason why I say that is because your batteries will determine how much power you're going to send to your home or your appliances. What you should do, or what I did, was I need to be able to show you at one point or put a photo on this video moment, but I made an Excel spreadsheet. I listed all the appliances that I expect to run. Make categories, you know, kitchen, bathroom, shed, you know, tools, a well pump, etc. Air conditioning, make that a separate system. Air conditioning and electric heaters are your largest electrical loads. I would avoid putting those on your solar system unless you had a really large system to keep up with it. Let me back up. When I say 20,000 watt hours total, I have the AGM, so 40 to 50%, 50 to 60% discharge, leaving 40 to 50% capacity. So if I had 20,000 watt hours and I could only use about half, that's 10,000 watt hours available. Back to that Excel sheet. List out all your appliances. List out the wattage and the amperage. Add all that up and design your battery bank around that total watt hours. When you put all those appliances and you line up all those items, you're not necessarily going to use all that current or power at once. Maybe think ahead and put a time slot in a 12 or 24 hour day. Use time slots of when you expect to use those devices and be real with it in terms of how long and when you plan to use it. Because like I said, you're not going to use, let's say, all 25, 30 appliances at once. You know, your blenders are going to be used in the morning, your well pump sporadically throughout the day, a microwave 2 to 5 minutes a day maybe, etc. List out your wattage, your amperage, and the amount of time that it's going to be running for. Okay, because if you have a 1000 watts microwave and you run that for 5 minutes, that's 5,000 watts used. Not necessarily 5,000 watt hours, just 5,000 watts used. So if I had 10,000 watt hours available, it's not necessarily 10,000 watt hours minus that 5,000 watts, you see, because it's not 5,000 watt hours, it's just 5,000 watts. If you use that microwave for 1 hour, then that'd be 1,000 watts times 60 minutes, and that's whatever that number comes out to, a lot higher than your battery bank capacity can afford to give. So everything is based on everything. Start with your battery bank and work towards your solar panels in terms of sizing, and then all the wiring, circuit breakers, that'll come last. Okay, once you figured out the size of your battery bank, whether you're going with a 12 volt, 24 volt, or 48 volt system, then you can determine what size inverter. Is it a split phase, or is it just a 110? You know, how big of a solar array you need. Again, I had mentioned there was a 4.5 sun hour where I was at, so that means about I have 4.5 hours of peak sun time to charge those batteries. If I designed my battery bank so big that it took 8 hours per day to charge, and I only have 4.5 sun hours, that means it would take 2 days to charge those batteries. That means you'd spend a lot more time with the unit off or giving you no power because you're waiting for it to charge. If this makes any sense, you want to get as close as a ratio as 1 to 1 as possible, meaning 1 day to charge your battery bank, or if you sent X amount of amps, it takes the same amount of time in return to charge your batteries. Trying to find a better way to make sense out of that. You don't want it to take longer to charge your battery bank than you're sending power. However many amps or however much power you're sending during the day, during those peak sun hours, you want to be able to charge equally as fast as you're sending power. So there you have it, my off the electrical grid DIY solar system, solar powered system. For you DIYers, if you have any questions or etc. that you'd like to reach out to me about and discuss, either put your questions in the comment section below the video, or perhaps I'll leave my email so you can reach out to me directly, and we can hopefully I can help address some of your questions or concerns if you're attempting to do this by yourself. Be sure to like and subscribe to the video or my account. All right, thank you. Bye-bye.